Good morning. We were discussing voltage regulators whose function is to provide a constant voltage. And the type of voltage regulator we are discussing is what is known as a linear regulator. That is, it basically works like an amplifier. Now, the efficiency of such a regulator is related to uh, how much the output voltage is compared to the supply and how much the load current is compared to the total current. Obviously, that's the definition of efficiency. Now, how much the input voltage or the supply is and how much the output voltage is may be part of the specification, but you would like to have the supply voltage to be as close to the output voltage as possible, right? It has to be greater than the output voltage, but if you minimize the difference, you will get the best efficiency, okay? And similarly, the load, the total current drawn to be as close to the load current as possible by minimizing the additional currents that you draw. Okay. Now there is another class of regulators altogether, which are called uh, switching regulators. Okay. They have in principle 100% efficiency because they use switches and lossless passive components like inductors and capacitors. So we won't discuss that. But to give a fixed voltage, they also employ negative feedback loops, and whatever you have learned about negative feedback loops can be used there as well. Okay. So typically, the power management in a large IC or any system will look like this. There may be a battery and it may have one or more switching regulators. Now these have clock inputs, okay, for switching, and the output of the switching regulators can go to linear regulators and so on, okay. And the switching regulators also can increase the voltage, not only decrease it. You can have voltages that are higher than the battery voltage, and actually this happens even in the mobile phone and so on. There are parts of the display or flash memory, etc., which need higher voltages, and there are others which need lower voltages. So typically what you do is you try to get to some lower value using the switching regulator close to the desired output voltage, and then this is the supply for the linear regulator. So we will be discussing only the linear regulator. Linear regulator is basically a negative feedback amplifier. Okay. You have a reference voltage usually generated from a band gap reference, and you scale it up to the right value by using an amplifier with some gain, whatever gain that you want. Okay. So essentially everything that you know about negative feedback amplifiers can be applied here. There are some special constraints in that typically for a regulator, the load current will be only in one direction and it can vary widely. So it does not quite operate in this small signal type regime where the increments are, the effect of increments are small. Okay. Only thing is you have to essentially you still do the same linear analysis, but you do it for the minimum load current, maximum load current somewhere in the middle and so on, make sure it works. Okay. So we saw that with this constraint, so let's say we wanted a 4.8 volts output, you start with a 1.2 volts band gap reference and a typical regulator, as we discussed earlier, consists of a single stage op amp which drives what is called the pass transistor. Basically, the load current passes through the pass transistor, right? And you implement whatever ratio you want. If you want K times the reference voltage, you have K minus 1 R and R. And you have your load. Okay. So now, of course, like any other feedback system, stability is a concern. So one thing is, of course, there'll be some parasitic here, and there'll also be a parasitic there. Okay. And there may be a bypass capacitor that is required simply to reduce the voltage fluctuation at the output. Okay. So these are all highly variable. There are some cases where you don't have the output capacitor. There are some cases where you do, and so on. Because one of the properties of this is supposed to behave like a constant voltage source. So that means that ideally this voltage should be steady. In reality, it will have some wiggles on it, depending on various disturbances in this power supply and so on. So one way to minimize that is to use a large capacitor. Okay. So now all these together can bring in some special challenges for stability. Okay. So how would you stabilize this actually? That is this negative feedback loop. If you have it like this, the way I have it looks like there are, and we have a large value of R, right, to minimize the current wasted in this. So looks like you have, what will be the sort of pole associated with this node? Let me call this CGP and this as CL. What is the, if you're in the loop gain, if you break the loop, what is the pole associated with this node? Not the closed loop pole, but what will it be? By now, I think you should be able to tell, right? What will be the pole? If you break the loop and evaluate the loop gain, what will be the pole associated with that? Will be? So basically, whatever the output resistance of that is, RO1, you will have something of that sort. Okay. What is the pole due to this capacitor? What will it be? So it depends on actually the impedance looking up that way, because this will contribute some resistance and this capacitor is also there. Okay. So, but if it will be of the order of and this R itself may have R in parallel with if this is a very large capacitor, it will be something like that. Okay. And of course, you have the pole associated with the output node itself. So what is that? What will that be? So one thing you have to keep in mind is that this MP, especially when you design it to pass large currents, its GDS, its RDS will not be very high. Okay, this won't be behaving like a current source. And typically, you also tend to use short channel transistors here, especially if you want a large current. Basically, you need a very large W by L, okay, to maintain the low dropout and support that current. So if you have very large W by L and you use large L, basically you have a very, very large device. Okay, so you tend to minimize the size of the device. So it's actually this device use short channel. So basically it behaves more or less like a variable resistor, okay, whose resistance is varied by the gate voltage. Okay. So there will be a pole here. The bottom line is there will be a pole here, which is in the loop gain. It will be of the order of 1 by RDSP times CL. Okay. And also it's not always clear whether the load will be modeled by a current source or a current source in parallel with some resistance and so on. Okay. But anyway, the bottom line is you expect at least 3 poles here, right? Not very high frequency poles, because you don't have very low resistances anywhere, right? So if you just make this, it is likely to be unstable. Also, this itself is variable, right? So if the load current is low, then this RDSP will be high, okay, and the pole will be at a lower frequency. If the load current is very large, then the RDSP will be low and the pole will move out. You have to take care of all those conditions. Yeah. Power? Yeah. Right. Typically, you operate from the same supply. That is, this will be connected to the same. Okay. So I won't go into the details of this. If you take power management ICs, you will see lots of details of different types of regulators for different specifications. Now, what is your first guess? If you just make this, what kind of step response will it have? Will it be well behaved? What do you think? 3 poles and not at not widely separated probably. So you expect a lot of ringing. So how will you fix this? What did we do when we had a multi-stage op amp? What was the ways of stabilizing this? Huh? Add a 0 where? What did we do in the earlier cases when we had a 2-stage Miller? What is Miller? Where? Yeah. So one possibility is you add a capacitor like this. Okay. Now you can try to do that. Of course, it has to, you have to choose the value that works for the highest value of CL as well as the lowest value of CL and so on. Now, one thing is this is not always preferred because one of the important criteria of a voltage regulator is power supply rejection. Okay, that is the gain from this VDD node to the output. Now, what happens if you use this Miller compensation is at high frequencies, you basically have this, right? You have the shorted Miller capacitor and whatever output you have. Okay. So that means that basically the gain from here to there could even be 1 or some a reasonable fraction of 1. Okay. So if you do this, you will get the same wiggle over there. Okay. So this Miller, the straightforward Miller compensation has a poor power supply rejection ratio. Okay. So you may not always use that, right? I'll just quickly outline a couple of possibilities. If it's okay for your application, go ahead and use it. You can use the Miller capacitor. Otherwise, you can try to actually have a large capacitor in place of CGP. That is, you add more capacitance. That is possible, right? You try to make that the dominant pole. Now, if the picture is exactly like this, you cannot do it because you will be have a non-dominant pole. I mean, you'll have a dominant pole here and also there. Okay, we'll see what to do about that. So the first thing is now one thing, of course, you will always do is connect a capacitor across this so that where do we add this? What does this do? The phase shift from there to there will be reduced. You have to make sure that this 0 is below the unity loop gain frequency so that basically at the unity loop gain frequency you have the capacitive divider, not the RC filter. Okay. So if I call this A, B, C, okay. Still, even if there is zero phase shift from there to there, you have a pole. I mean, let's now, I mean, I said it's unrealistic, but if you think of this MP as a current source and this also as a current source, you have two poles at very low frequencies. Okay. So now it turns out that the output bypass capacitor. So when you use a large capacitor, many times you use microfarads of capacitor, it will have its own series resistance. Everything will have it. I mean, you connect wires, it will have a series resistance, but a large capacitor will have more. So this is called effective series resistance or ESR. Okay. So what happens because of this? So if you look at let's say this common source amplifier, and if you plot the magnitude of the gain, what will that look like versus omega? What will be the gain at very low frequencies? Let's say the transconductance of this is GMP, and we can neglect the RDS of that. Okay, for now, just for writing expressions. If it is there, you put it in parallel, that's all. What will be the gain at very low frequencies? GMP times KR. Okay, and what happens after that? So basically, when the impedance, we'll assume that this effective series resistance is small. After all, this is supposed to behave like a capacitor. So when the impedance of the capacitor becomes lower than this, K times R, so basically that will happen when approximately. So then the magnitude will start falling. And if you look at the phase, so the phase will be 0 here, and then it will go to minus 90. Okay. It actually starts from this is the phase of minus V naught by Vg, because it also has a negative sign. I'll ignore that and write this. So there is a phase lag in this region. But then what happens at very high frequencies? What happens at very high frequencies? Basically, this becomes a short circuit and you only have RESR as the load. It will be RESR parallel to this, but if this is very high, it is approximately RESR. So this frequency will be approximately 1 by CL RESR, and this gain will be GMP RESR. Okay. So again, the phase shift comes back to 0, right? Now, if your unity loop gain frequency is going to be there, then again you don't have any problems, right? So basically one way is, if you have to use a very large capacitor and you cannot use this Miller compensation, you have to make this the dominant pole. Okay. And you have to position the unity loop gain frequency where the bypass capacitor behaves like a resistor. Okay, because if you try to do it here, you have 20 dB per decade roll off of this amplifier, another 20 dB per decade roll off of that amplifier. So you'll have 40 dB per decade roll off and it will not be stable. Okay. So you have to go, you have to adjust the parameters such that the unity loop gain frequency is where from here to there you don't have any phase shift, excess phase shift because of the capacitor. That will happen if you have sufficient effective series resistance. If it is not there, you may have to deliberately put it. Okay. So at that point, what happens is this stage is not really giving you a lot of gain, right? GM times ESR will be quite small. Only thing is that you try to get as much gain as possible from this one. So you may have to use cascodes, even multi-stage there, but try to make this the dominant pole by adding a capacitor. Is this okay? So principle wise, there is nothing different. You have to have a dominant pole and all the non-dominant stuff should happen after the unity loop gain frequency. Or even if you have poles and zeros before the unity loop gain frequency, if you have n poles, you should have n minus 1 zero so that you cancel them off. Right? So that around the unity loop gain frequency, you have 20 dB per decade roll off. Only thing is, because of practical constraints, which one you make the dominant pole here may be different from what you do in an op amp. Okay? Is this fine? So if you want to design a regulator, first, especially for a relatively high current, first you design the pass transistor so that it can pass that current with the required dropout, and then you design everything else around it. Okay. Any questions about this? I will upload an assignment on this. It is not for submission, but you can try it out if you wish. Any questions about voltage regulators? This is not the only way to make a voltage regulator or a pass device. You can do other things which may have other better properties. For instance, you can use an NMOS pass device. Okay. This is the band gap reference, and you can have a gain. Okay. And you have your load and the capacitor and so on. Okay. The earlier one we had a PMOS pass device. The only difference between this and the what did we have? We had a PMOS pass device, and of course, with the PMOS, the signs must be like that. Both give you the same output voltage, K times VBG, right? So what are the pluses and minuses of the two circuits? What might be the advantage of the upper circuit? So one thing is that even in open loop, this is a source follower, right? So that means that this resistance is already low, and when you put it in closed loop, it will become very low. It will be reduced by the loop gain. Okay. So this can give you much lower DC output resistance, because after all, you want to make a voltage supply, that is a voltage source, right? Something that mimics a voltage source. So that means that your output resistance should be very low. So this will do that. Whereas here, it may be higher. The only thing is, of course, the low frequency output resistance comes mainly because of the loop gain, not because of whether this resistance is low or not. So by increasing the loop gain, you can lower that. Okay, because open loop, what will this be? It will be 1 by GDSP. Okay, this will be higher, but the loop gain will suppress that. Okay. What might be on a, what are the other differences? So the power supply rejection here is likely to be higher. Even normally, if you change the drain voltage in a source follower, the source doesn't change, right? It will change because of its own RDS, but that factor will be very small. Okay. It will have higher PSRR. Okay. What else? What else might be the difference between the two? Yeah, so that is fine. I mean, we have to take care of that. You have to do what you have to do for that one. So if the upper circuit is so good in every way, why did I start with the lower one? What is that? Okay, so what aspect of in terms of the voltage regulator parameters, what does it affect? What did we discuss earlier? If I want to get, let's say, 4.8 volt or some output, okay, V out, the same output voltage in both cases, what might be the difference in these two? What is that? Lower loop gain. Why? Loop gain, let's say you can design the first stage to get whatever loop gain you want, DC loop gain at least. That's not a big concern. Yeah, I would put it differently. The minimum supply voltage required here is, right? Basically, the dropout is whatever voltage you need to maintain there. That is smaller here than there. What will be the minimum supply voltage required here? What is the minimum supply voltage required there? Huh? What is it? I mean, is it different actually? Is it? VTN. Why? Yeah. The thing is, this is of course operating with the same supply. Okay. So now what is you need to have VGSP there for it to be conducting. And what is the voltage required here? I mean, what is the requirement of this stage? You need at least a VD sat of its own device inside, right? What is the best case? What is the highest output this can provide? See, the thing is, there is only one device. It is possible that you have V out here and you have V out plus VD sat in there. This is possible. But if this has to happen, what will be the gate voltage? It will be at V out plus VD sat in plus VT. So that will be above the supply voltage. Okay, above this supply voltage. So the previous stage has to provide that. If the previous stage is operating from the same supply voltage, that is not possible. Okay. So this is a problem with source followers, right? The source followers have poor swing limits. I think we discussed this long back. Of course, then there is the problem of body effect as well. If you have NMOS source follower and the source is tied to ground, VGS itself will be larger. Okay. But the point is, it will be, if I call this op amp as A1, it will be V out plus VGSN plus, I'll just call it VD sat, but I think you know what I mean. It is the VD sat of A1. Okay. So that's basically the difference between VDD and the highest output of the first stage. Okay. So you can see the dropout here is a lot larger than the dropout there. Okay. So if we consider VD sat to be 0.2 volts, the lower circuit can be made with a dropout of 0.2. That is minimum difference of 0.2 volts between the supply and the output. What will it be for the upper one with the normal parameters that we have been considering? Let's say VD sat is 0.2 volts everywhere. What is the minimum dropout? What are the parameters that we normally use in every test and exam and assignment? You used it. Threshold voltage is 0.5, 0.4. Where was this? I don't know. I can't recall a single problem in which it was 0.45. What is the minimum dropout here? This is the dropout. What is the minimum dropout there? 0.9. Okay. If we assume that this has a VD side of 0.2 and whatever is inside the op amp also has a VD side of 0.2. So this will be okay. So that you can see it's a substantial disadvantage when you're looking for small supply voltages. That's why you don't use that. Most of the time you end up using a PMOS pass transistor for positive supplies. Okay. Any questions? So that's the very bare bones treatment of voltage regulators. It's a negative feedback loop. Oh yeah, one more thing I wanted to mention is that this let me take the PMOS case, which is more typical, right? So one of the tests that you do is you step IL from low to very large values and vice versa. Okay. How do you expect the settling to be? So this is IL, right? And if you look at V out, ideally it should be at K times VBG. So what do you think happens if IL stepped up and stepped down like this? What happens if IL is stepped up? What happens when the IL is stepped up? What happens to the output voltage? What do you expect? Will it go down, go up, not do anything? Down. I mean, that's what you expect, right? If you draw a current, it will go down. By the way, that's not what is called undershoot. This, if you have the starting point and ending point, the starting point can be above or below the ending point. So if you go in the wrong direction, this is what is called undershoot. And this is overshoot. Similarly, on the other side, this would be undershoot. And even if this goes below this, this is called overshoot. Overshoot is simply going beyond the target in the right direction. Undershoot is starting off in the wrong direction. Okay. So you expect this to dip down like that, right? Initially, it will jump down. Okay. In fact, if the capacitor is like this, all this current will just come out of the capacitor. It will dip down some. Then what happens after that? It will rise. Where will the current come from? So initially some charge is taken out of all the capacitance at this node, and then this will supply the current, and depending on the phase margin, etc., okay, it will settle in some way. Let's say it settles like that with a little ringing. Okay. Now basically this ringing depends on, let's say let me call this IL min and IL max. If you want to predict how it settles, you have to calculate the small signal parameters and the loop gain. At what operating point will you calculate the loop gain? Because you have to calculate small signal parameters and they are a function of the operating point. What will be the operating point for calculating this settling? No. So whether this rings or settles cleanly depends on the loop gain, which in turn depends on GMs inside there and so on. Okay. Where will you, what operating point will you calculate the GMs at? That's not correct, right? Because as you step this, the current increases here. So this settling mainly depends on the operating point of MP at very high currents. Okay. So basically, I mean, if it's a very small signal step, of course, you have the operating point and there you calculate. So what I want to distinguish is the two cases where if you have a small step, if you have a positive step and a negative step, the response will be equal and opposite, right? That's all. That is linear. What I was trying to point out is this can be quite nonlinear, because what happens now when the current steps down? When the current steps down, basically this can cut off initially. Okay. And the settling can be quite asymmetrical. Okay. Because you have different operating points. Now, if you have a small signal step up and step down, they'll be symmetrical, right? You understand? If it's actually all I'm saying is it's a nonlinear system. That's all, because current level is changing substantially. Okay. Because if you do have a linear system, whatever happens at the positive step, at the negative step, exact opposite of that happens. That's all. You don't need to calculate both, right? To calculate the response to negative step, you just whatever response you had for the positive step, you put a minus sign on it, and that's all that's there. Whereas here, it may be different. Okay, one could be fast, the other could be slow, and so on. When? Which one? Right. So, but basically, let's see, or maybe I got it the other way around. So, what happens is when IL decreases, what happens to the output voltage? It will rise. So, this voltage, it will rise. So, it will, if this rises substantially, it will cut off that transistor. So, then basically, it has to kind of settle through this and then okay. Any questions on voltage regulators or anything else? Voltage references? No, I mean, in general, you have to take at least some points in the middle. Of course, taking every point, it's a continuous thing. It's not possible, but at least you have to take a few points. It's not necessary that the worst case be at the extremes. With some combination of parameters, the worst case can be at some other place as well. I don't know. I think, at least I don't know about that. I think it's circuit specific also. It's very much topology specific. Huh? Yeah, it is. It can slew, right? Here it can very much slew because, see, you don't have any bias current normally, right? So slewing happens when something cuts off. It is slewing. Right, right. Yeah, when the IL steps down to negative values, basically it has to slew until it becomes correct. Well, the formulas for slew rate is different, but basically it is the same phenomenon that some transistor cuts off, so you cannot charge. Basically the charging rate is limited. Okay, I mean you can't use the two-stage op-amp formulas here, but the phenomenon is the same. Right. Yeah, that is possible. I mean, but the first stage op-amp is driving the gate capacitance of first stage. That slewing is also possible. I mean, you have to see these things depend on the conditions, but yeah, it is possible to put the first stage into the switched mode. That is possible. I mean, you don't need to like basically see finally what matters is the total settling time and how much the voltage changes from the normal value, right? So those things you have to satisfy. After that, nobody will ask about the slew rate and so on. Okay. So we have come to the end of the course. The goal I had said was to learn about negative feedback for controlling the output, and we'll discuss amplifier voltage references and voltage regulators. And these we went through the components on an IC and what uncertainties you have to deal with. And mainly, most of the course was about how to implement negative feedback circuits on an IC, basically, which is how to make an op-amp, right? Now, the single stage op-amp and the multi-stage feedback, that is Miller type op-amps, you are already familiar with. Only maybe extending to multiple stages may not have been so clear, but we saw it from another viewpoint also. And then the feed-forward op-amp is probably new. So we looked at different types of op-amps, different types of single-stage op-amps. There's multi-stage feedback op-amps and feed-forward op-amps. And most importantly, fully differential op-amps, which are very widely used. So they need common mode feedback. Again, principle-wise, common mode feedback or any other feedback, it's the same. In fact, we saw that most of the equivalents of common mode feedback turn out to be either one or two stage op-amp equivalents, right? And of course, now these are something specific to IC that you have to calculate the effects of mismatch and noise. Noise was likely unfamiliar. So they all can be calculated in the same way, mismatch and noise. And slightly related is also distortion. That is, you're not likely to use it very often, but you want to calculate something finer than the swing limit, but you still want some idea of the nonlinearity. But you don't want something as crude as swing limit to saying that, oh, this is the maximum I can apply. Because in reality, as you increase the signal amplitude, it's not that it behaves linearly up to some point and then it stops, it starts misbehaving. So the distortion components go on increasing. Now you know how to calculate that, but the most important part for all of them is linear circuit analysis. You convert everything into the small signal linear equivalent circuit and do various things with it. Okay. So that you should be fluent with. And I had actually mentioned this that we will go through the voltage and current references that we have done. And these, if there is time and there is no time, so that's fine. You can go to other courses for these circuits. Okay. And basically, this is what you need to know by now, right? And I think with all the assignments, you probably know these things. Filters, yeah. Basically, filters, continuous time filter. Yeah, right. So you can, in a given process, with a given power dissipation, you can get a higher unity gain frequency with the feed-forward op-amp. I think that we had briefly discussed in one of the lectures. Basically, so the unity gain frequency in a Miller type op-amp has to be some factor less than the parasitic pole. The parasitic pole is a function of the process, right, and the load capacitor that you have. So that you can take as some sort of process limit. So let's say that is arbitrarily, I'll say 1 gigahertz. So that means that your unity gain frequency can at most be, let's say, half a gigahertz. Whereas in feed-forward op-amps, that parasitic pole is like the unity gain frequency. So that is the limit. So in this example, for instance, you can probably design unity gain frequency all the way to 1 gigahertz. That's why. But of course, I also mentioned this feed-forward works best when you have unity feedback around the op-amp. So that means that it has to be either a unity gain amplifier, of course, that's a very narrow range of applications, or more likely an integrator. You have R and C, there the feedback fraction is frequency dependent, but around the unity loop gain frequency, that C will be a short and you have unity feedback. Every active filter, or there is a large class of active filters which have this type of structure. So there the feed-forward op-amp is more power efficient compared to Miller op-amp. First of all, by definition, the small signal analysis means there is one operating point, and after that, there is no further change there, right? That is, you calculate the small signal parameters at that operating point. So if you are considering, first of all, threshold voltage change, I don't know, you probably mean by body effect or what is it? Yeah. So that body effect itself can be taken as some incremental quantity. I mean, VSB can be taken as some incremental quantity and you can do incremental analysis. Or of course, if you are considering it as change in threshold voltage, that is basically like large signal analysis, right? Completely dependent on the problem, right? Right, right. So see, if the threshold voltage is varying with signal and it is significant, then you have to go to the nonlinear analysis or more likely simulation to find out what's happening, right? But main thing is to see, the main objective of all these design principles and calculations is to see in which direction to steer your design. Okay, not necessarily to calculate to the third decimal what the swing limit is. Swing limit itself is such a crude measure, right? So let's say you design it without including this body effect. You think that you can have 500 millivolts of signal, and in simulation you find it is less. Okay, and you also now with further simulations you can find that this is because of VT change due to body effect. So then the one goal may be to predict this, but actually the more important goal for a designer is how to get it back to 500 millivolts. Okay, so that you can do now based on everything else that you know. Okay. Huh? Huh. Right, right. That you can do by simulation, right? I mean, that basically the idea is, see, those things, the cascode bias and so on. So you have to adjust based on simulation. Of course, in the assignment, you have just one value. In reality, you have to make sure that it works across process and voltage corners and so on. So you have to generate that voltage so that under all the conditions, as the temperature varies over whatever range, as the process varies from the VT itself will vary, even with process, even without body effect. The transistors do remain in the desired regions of operation. Okay. Now, if it is one particular corner, like in the assignment, now whether you have body effect or not is irrelevant. The only thing is you don't know what the value of threshold voltage is, but you can, in the replica bias also, you can try to have the same body effect and then get that. Okay. But the main thing in design, when you come to designing real circuits, is to make it work for all the corners. Okay. Not have or have. No, I had put some simplified circuit where I had put a current source in the middle of the diode connected NMOS and PMOS transistors. Anyway, you can't make that. I just put it as a simple thing. But if you want to put different branches, that is perfectly fine. No, no, I mean, you can't make that floating current source, right? See, that's a representation that simply says that the same current is flowing through the diode connector and this diode connected transistor. If you have two separate current sources, the same thing will happen. There's no change at all. Why? I mean, if you have the same currents, why will they be different? If they have the same current value, they'll not be different, right? See, here you are using an ideal current source. If you use an ideal current source, one or two, what difference will it make? That's what I'm saying, man. There is no floating current source, right? You can't do that. Okay. So that's just a representation of current flowing there. That's all. Okay. So these things, I think you know. The last one, like I said, I'll upload some assignment which you can try if you wish to. And this is a voltage regulator with a reference. These are all different feedback amplifiers. And these are circuits that we have not dealt with, like a current steering DAC. So this consists of differential pairs. So even if I didn't say the word DAC here, if you see a differential pair anywhere else, you know what to do with it. Okay. Similarly, active RC filters, you don't know the details, but you can design op amps for this. Okay. So, but most important thing is those of you who go to design, either for circuits or anything else, or any creative field, you should be able to comfortable with trying multiple options and trial and error approach and so on. So this persistence is very important, right? These are not like problems that, okay, in 15 minutes or whatever number of like some short duration, you will get the answer. It's more like random walking through different possibilities. So what you know will help you to move in the right direction. And if you know a lot, then you will move maybe more rapidly in the right direction, and also eliminate the alternatives that don't work very quickly. Whereas if you know a little less, maybe you try a lot of those things and spend more time. But the thing is whether in either case, you will have to you will actually not, you will have to have, you will end up going back and forth through the design. Okay. So you can ask any of the TS, they are doing designs. And if you ask them what they were doing in the first month of the project, second month, third month, and so on. So it will be, it won't be like this. It will go back and forth lots of many times. Okay. And of course, as you learn, you should try to develop intuitive thinking. That is, there is a systematic way of doing that. You try to always try to find the answer before you calculate it. Okay. And if you find a difference, it means that either your intuition is wrong or your calculation is wrong. Then you try to fix that. Okay. So this takes time. So that means that you can't do 100 different things. You choose few things and you do them well. Okay. And of course, you need to be open-minded and things like that. You can't say that, oh, I will not use a PMOS differential pair because he said so, right? So a lot of these design principles are not rules, or they're not like mathematical laws or physical laws, right? So when I say, oh, the dominant pole of an op amp is at the output of the first stage, you shouldn't think of it as some sort of religious prescription. Okay. So there may be some case where, depending on the load and so on, the dominant pole of the op amp might be the output node. Okay. If you have very large CL and something like that. Similarly, GM1 being smaller than GM2, that is generally true, but who knows? Maybe you will find some weird case where that is not. Okay. So you shouldn't have to, you shouldn't tie up yourself with something that was applicable in a different context. Okay. So a lot of people have found new things by simply relaxing some spec. What happens is, as engineering develops, there will be some design principles that have been developed for some context, and people will keep following it. And sometimes that can be constraining. Later, somebody will figure out that, oh, the reason we are following this rule is because of something that's not relevant anymore, right? And then that's it. Like you can find new stuff. And thoroughness is very important. Again, this is not only for circuit design. This is for everything that you do, right? So basically, some people evaluate themselves on how many things you do. I definitely don't. It's more important to do things well. Okay. You have to do many things just so that you have options, but you don't have to do 100 different things to have 100 different bullet points on your resume. Okay. Whatever you do, you have to try to do it well. Okay. And of course, other op amp architectures with these principles, I think you can find out. So this is a pseudo differential inverter. This type of op amp, this quote unquote op amp, has become popular because you have only two devices. And if your supply is only 0.7 volts, this is more or less the only circuit you can build. But this doesn't have common mode rejection, but you can build common mode rejection. You may have seen this problem in either analog circuits assignments or not in this, I think. In the analog circuit assignment, it may have been there. So it does provide common mode rejection. Okay, and other feedback systems like phase lock loops. There is actually a separate course on phase lock loops if you wish to take. Saurabh teaches it, and then Delta Sigma, Shanti teaches the course. So these are also feedback loops. The basic negative feedback loop stuff will help you, and of course, the goals of those feedback loops is to implement something else. Okay, and then one interesting thing which I wish I had some time for is to not make only analog loops, but you can also make it in a digital way. Okay, so that is in the voltage regulator, instead of having an amplifier to control the gate of the pass transistor, you can have a digital to analog converter. If the output voltage is less than that, you can keep on stepping it up and so on. Okay, so those things are possible. So these are all, I think we have more than enough courses to satisfy your need if you feel like studying analog circuits. And next semester we'll have IC design and testing and a number of other courses. I highlighted this because I teach this, but there are lots of others as well. Okay. So